All right, so jumping into chapter 5 here, and now we talked about this a little bit a couple chapters ago with z-scores just to compare two different values. We're going to continue with this idea of normal distributions and continue to dive deeper into this idea. This is where our z-scores really come into play in our normally distributed data. So, and then with March and St. Patrick's Day, some of you guys may have found a 4-leaf clover out there. If you did, the tendency is to try to keep that because of the luck that it has, and so people will try to dry out flowers or whatnot. A common thing for 4-leaf clovers, weirdly, is people try to iron them. I highly suggest you do not iron your 4-leaf clovers because you definitely do not want to press your luck. All right, 5.1 notes. Okay, so we're going to look at how do we interpret graphs with normal probability distributions. So we're going to use this normally distributed, our kind of z-scores and standard deviations in terms of finding probabilities of events happening, and in that, finding areas under that normal curve. So what is normal distribution? So here's an example. So when a doctor takes our blood pressure, normal is from 110 to 140, and the normal interval for a person's triglycerides is from 20 to 200 milligrams per deciliter. So how does one determine the so-called normal intervals? And so often we have these ideas of continuous variables or distributions that are bell-shaped. So you may have heard of a bell-shaped curve, and what those more appropriately named are approximately normally distributed variables. These shapes are called normal distribution or a bell curve or a Gaussian distribution. Remember that these are continuous variables, and variables can assume all values between any two given values of the variable. All right, so a few examples here: heights of adult men, body temps of rats, cholesterol levels for adults. All right. And so as our sample size increases, if you're building histograms out of it, look more like a normally distributive curve, right? So this last one is our normal. So you get 100 and about like that, doesn't tail off as much. Now you get more of that, and then even more so there. And so as your sample size increases, those bars, our width, our bin width, and our classes decrease and become a whole lot more of this normal distribution here. Now, there's never a perfect, just like when we kind of talked about some shape stuff that we say roughly symmetrical, because rarely, if ever, will you get perfectly symmetrical data, especially in this normally distributed curve. It is a theoretical distribution, allows us to talk about a lot of things, and it does apply quite a bit, but it is never going to be a perfect fit. And so I want to make sure we understand that. And there's not going to be a perfect fit. There's always a little variance that takes place in there, because we have variables, and variables don't fit perfectly. And now, normal distributions get used in a lot of areas, right, to model measurements, industry, business, because it's a continuous probability distribution for a random variable. And then we call this distribution a normal curve. So a couple of properties we talk about here, all right? And so we've talked about mean, median, and mode. Right? They are all equal in a normally distributed data because as you look at this, it's roughly symmetrical, and in this case, the theory of it is perfectly symmetrical, which means all of those, mean, median, mode, are going to be all found right there exactly at the center. And remember, that's our symbol for mean. And we said it is symmetric about the mean. Then the total area under the curve is important. Okay, it's equal to 1. So when we add up all those areas, that's how we can find the probability, because 1 and a percentage then turns into 100%. And so there is our probabilities. And so 100% of all outcomes can be determined under this normal distribution. And then one small thing, doesn't come up a huge amount, but it will never actually touch the x-axis. It gets super close, and as it extends further and further away from the mean, but it will never actually touch the x-axis there. Right? That's kind of our asymptote idea, which is concept of a line gets super close, but never will actually touch that line. All right, now we have a definition here. Now, I'm going to highlight this in red because that's what you're probably seeing looking at that thing. The good news here, just want to show it to you. You actually don't need to know this. All right. We're not going to use that formula to calculate it. We're going to apply and look for some other things in some other ways. All right, so the shape and position of a normal curve depend on two parameters, the mean and the standard deviation. So not every normal curve or normal distribution is built the same. So below we have two pictures. We have curve 1 and we have curve 2. Notice the means are exactly the same. All right, remember that's our Greek symbol mu for mean, but we have different standard deviations. Standard deviation of 1 is greater than the standard deviation of 2. Remember, standard deviation is one of the measures of variance, so how spread our data is. Okay? And so from there, notice curve 1 has a greater standard deviation, and so that blue line is then more spread out in this area here and not as peaked as high, where curve 2 is squeezed more because how spread out our data is smaller, and so it's much more steep of a curve versus curve 1, which is a little flatter. And so as we look at that then, right, the standard deviation, the more dispersed or spread out our distribution is. So a huge concept to understand as we're looking at ideas and comparing graphs. So one, which graph above has a bigger standard deviation and why? Well, we talked about that already. It is curve 1. It's given to us, so we'll state that obvious there. But if we're just looking at the pictures themselves, we would say curve 1, because the slope of the curve is less steep and more spread. All right, now let's look at number 2 here. Okay, so which graph has a greater mean and which has a greater standard deviation? So let's look at two things. So remember our mean, all right? So that symbol again, so the mean of A, how does that compare to the mean of B? Well, the mean is going to be exactly in the center, so our A is right about there, and then our B is going to be right at our peak, and so right about there. So in this case, I would say that our mean of A is going to be greater than the mean of our B. Now standard deviation, so now we're looking at our standard deviation of A. versus the standard deviation of B. Well, when I look at A, those are pretty steep, and that height is taller than B in relative, right? So that's short, and those sides are definitely not as steep. And so I would say the spread, our standard deviation, is greater in graph B. And then answer 3, we kind of drew those lines already. So our mean of A is 15, whereas the mean of B is 12. Okay, so let's summarize some of these theoretical concepts here. Right, so normal distribution is often called a bell-shaped curve. It's a nice reminder of what it visually will look like. The mean, median, mode are equal, and they're located at the exact center. So bell-shaped, mean, median, mode are equal, and are located at the exact center of our distribution. It's unimodal, saying one peak, and that why only one mode there. The curve is symmetric about the mean, which is equivalent saying the shape is the same on both sides. The curve is continuous. There's no gaps, so that's why histograms are used well with that. We fill all of those in. You can do normal distribution, talk about normal distribution of dot plots and other things, but once we transfer it to a normal curve, then it all gets filled in. Okay, because remember the area underneath that curve has to equal 1. And that brings us down to this concept, 1 or 100%. Now, from there, we then take the next step out is these standard deviations, so how far out from the curve it is. And we use those to really talk about our percentages of data. And then there's this really cool one here where data happens quite a bit. And so we have this area under part of a normal curve lies within 1 standard deviation is about 68%. 2 standard deviations is about 95%. And then 3 standard deviations is 99.7. We'll talk about this more in detail. We call this the 68, 95, 99.7 rule. It has a more official name, but I like this one because it helps you remember what those 3 values are. And you can see here in this that there is 1 standard deviation. And they give the exact value, but we just talked about it as 68.26, but it's about where you would be. And then if we extend out to 2 standard deviations, we add in that extra. So that space is about 95%. And then all the way out to 3 standard deviations is 99.7. So you can see why, even though we never touch the x-axis, that once you get outside of 3 standard deviations, there's only 0.3 outside of that. And so really on this side, it's 0.15. And on this side is 0.15% of your data. So that's really small. So that's so close that unless you have huge amounts of data, there's not a whole lot of numbers, if any, that are outside of 3 standard deviations. That's unusual. Even outside of 2, that's why in some previous chapters we've talked about outside of 2 standard deviations was unusual data. And a couple different examples here again, showing, hey, we have 3 sets of bell-shaped curves or normal distribution with the same means, but slightly different standard deviations in the first 2. But then in C, right, that we have a mean that's less, but the same standard deviation as in B. And so you can see how those things shift and how they compare to one another.